Right. On to rate law in kinetics. So a really great chapter here. So what we're looking at is that we have these different reactions, and then how can we figure out how fast it'll go or what's happening with it? And so we can vary the concentration and then see the effect. Higher concentration, more collision, the rates increase with it. And later on, we'll get to this idea of a catalyst. But at the end of the day, what we want to understand is what's happening at the molecular level there. All right. And so that will get into mechanism. So for now, we're just going to observe the properties and be able to understand what's that relationship between the concentrations of them and the observed rate that we see. And so in order to do this, then for a general reaction like this, looking at only the reactants, then we get this rate expression. And so we have the first kind of calculations is given K, the concentration A in the order, B in the order, we're able to solve them for that rate expression. Um, Another thing that you will do that's really common, it's built into the common problems that we're going to do, the big calculation we do at the end, is to do this. Now, given the rate, solve for the rate constant. And so here you would know this, you would know this, and this, this, and this, so you can rearrange and solve for this. What's unique for that, though, is those units are going to vary. It's really an odd situation where the units change, and so it depends on these orders. And now the last one, the big calculation for this video is how do we solve for these orders for A and B, all right? And so that'll be a mechanism we call method of initial rates. So here on the website, you'll find a calculation like this. You'll see rate. Well, now, how in the lecture I said there's a lot of different rates. You should start getting comfortable with it. Now at this point, you should be comfortable. Like, what is it asking for? We want to solve for this rate here. All right. So we know the concentrations and we know the orders. This number here doesn't matter. It just means that that rate is dependent on it. And we have K, the rate constant, which the units will vary, as like I talked about in the last one. So this should be an easy one. Just plug it in and solve for rate. Another form of this, though, is to solve for the rate constant. And this is what you're going to do at the end of the big calculation today is that we know the rate for it, we know the concentrations, we know the orders. So here's the rate of it, the reaction rate. So then you can solve for K. So hopefully when you plug it in, you can get this number. And if not, we can meet and talk about it. But on to the big thing is be able to determine the reaction order. And so we call this the method of initial rates. So we're going to compare how those rates change when changing the concentration of one reactant and keeping the other one constant. And what we're going to do is we're just going to look for these simple relationships. If doubling A and keeping B constant doubles the rate, then that means that the order is 1. And so we're going to have either order 0, 1, or 2. Those are pretty much the limit of what we do. And then you might have scenarios where doubling the concentration A leads to quadruples the rate of it. And you're going to see on the next slide how this then would give us the order must be squared. So those are the big empirical things that you're going to want to take away from it. So on the website, I don't have this as robust. I do this on Excel for the exams and quizzes. And so that's what I'll show you here today. These numbers don't come out as nice, so you have some rounding. I need to work on it and get it better. But here I'm just going to overlay them on some there. But if you cycle through, you should be able to get the process down. I just need to fix that. So if we look at this, then we have 3 different reactions, and we're going to then try and find these orders for these rates. So the idea is that we're going to choose rates, and we're going to have it so that the rate of one experiment is greater than the rate of the other one. And in doing so, when we divide this, we'll get an integer. If we can do the other way, it works out, but you get a fraction or decimal, and people just don't like that. So if we look up here and we want to vary one and keep the other one constant, then if we use experiment 2 over experiment 1, then we can see that the rate is bigger. So this will come out to an integer. We have K on top and bottom. This will cancel. We have 0.6 raised to the power we're trying to solve for versus 0.3 to that power and 0.2 over here. So a lot of stuff falls off and it reduces down to 2 here and 2 here raised to the power m. And now we get that simple approximation where m is 1. And like I said, we're going to have the scenarios where m is 0, 1, or 2. So you can simply just plug in, do those three, and see it, but you're going to instantly get that. So so now we know the order of this one or here, and so we just need to find the other one. We choose another two experiments, and again, we want to keep them the same and then vary this and see how it changes. So now we can see this would lead to 6 over 2, and this is the same, so it's going to fall off. So it simply reduces down to 3 over 3 to the n. So again, n equals 1. So now that we have this, then we can plug in, we can choose any one of these and do like we talked about before. We know the concentration, we know the order, so we can solve for K. All right, so hopefully it's a kind of completes the picture and you're able to do all these calculations.